Hello, everyone. My name is Zhang Shen. I'm a PhD student at Syracuse University. My presentation today is about the effectiveness of multi-scale IAQ control strategies for reducing the risk of airborne transmission of SARS-CoV-2. I guess we are already very familiar with the COVID-19 pandemic. Right now, due to the emergence of some new variants, we are still facing a very severe condition to fight against the pandemic. Therefore, it is still essential to control the virus spreading. For a respiratory disease, there are typically three different ways to spread out the virus, including formaldehyde route, droplet route, and airborne route. Airborne transmission occurs through the aerosols exhaled by the infectors through coughing, sneezing, talking, and breathing. The exhaled aerosols are typically smaller than 5 micrometers and can remain suspended in the air over a longer time and distance, traveling with airflows and air circulations, which makes it has the potential to infect more people than droplets and formaldehyde. Regarding SARS-CoV-2, there are many strong evidence supporting its airborne transmission. It is widely believed that airborne transmission is a potential transmission in indoor environments. Some studies even suggested that it is the dominant transmission in indoor environments. According to the survey on COVID-19 outbreaks, it can be found that most outbreaks happen in indoor environments, including both home-based scenarios and transportation scenarios. Based on the infection data in different indoor scenarios, we observe that the major hotspots include long-term care facilities, K-12 schools, restaurants, retail facilities, offices, and other scenarios. Viruses spreading in these scenarios need certain studies. In order to mitigate infection risk and prevent transmission through the airborne route, some IQ control strategy can be applied in the indoor environments, including source control, ventilation, and air cleaning. This control strategy can be performed at different scales, from building, room to personal microenvironment and breathing zone. The application of IQ strategy can bring benefits to infection risk reduction, but will likely require more cost and energy consumptions. Therefore, in order to analyze the effectiveness in practice, both benefits and costs of IQ strategy will be considered in this study. So widely used wealth rate model will be used to estimate the infection probabilities due to airborne transmission in the indoor environments, with an assumption of steady state and while mixing indoor air. The infection probability is estimated based on the inhaled dose of quantum of infectious particles. The equation depends on the source emission from the infectors and the dilution due to ventilation or disinfection, and also the inhalation by healthy people. The equivalent ventilation includes the ventilation from the HVAC system, the disinfection of UV system, removal due to particle deposition, removal by air cleaners, and natural inactivation of the virus. The ventilation supplied by the HVAC system can be divided into the outdoor fraction and also the recirculated part that goes through the filter. Because the equation has a well mixing assumption, we use the factor of ventilation effectiveness in the original equation to study the performance of different air distributions in the room. For example, displacement ventilation and personal ventilation may deliver more fresh air to the breathing zone before it was mixed by the contaminated room air. Therefore, they will have a high ventilation effectiveness in the equation. Based on the infection probability and the total number of healthy people, we can calculate the new infection number and also the basic reproduction number, which stands for how many people a patient can infect. One important factor in the equation is the contagion rate. This factor was proposed to quantify the emission of infectious particles. It can be estimated based on the viral load model, depending on the viral load, primary rate, and particle number and size distribution. Based on our assumption, we estimate that the mean quantum generation rate is around 58 quanta per hour for sedentary and light activities, and much higher for higher intensity activities like singing or doing exercise. It is generally consistent with the literature data. Because the virus can transmit readily in many public spaces, we established the baseline indoor environments for typical indoor scenarios. As you can see in the table here, including 13 building scenarios and 5 transportation scenarios. Each scenario includes several spaces. The baseline cases are created based on the DOE prototypes or other design guidelines like ASHRAE 62.1 standard or the data from literature or practices. This study evaluates the performance of different IQ control strategies on infection risk reduction. The study strategy include reducing occupants for the building and improving ventilation system, like increasing ventilation supply effort rate and elevating outdoor air fraction for the HVAC system, or just using higher efficiency filters, or use advanced air distribution like displacement ventilation and personal ventilation, or using standalone air cleaning technologies like portable air cleaners or upper room UVGI systems, or just wearing masks. The infection probabilities are calculated using the Vasarely model. Then a stochastic approach is applied to consider the possible variations of the inputs. The detailed information of the baseline and proposed cases are shown in this table. The HVAC system in the baseline case using a MERV 8 filter with 25% outdoor air fraction and its mixing ventilation. For proposed cases, the control strategy will be applied one by one to study the individual performance on risk reduction compared to the reference case. Here are some results. The infection probabilities and the reproduction number of different baseline cases are calculated and shown in the table. We can observe that spaces in long-term care facilities, colleges, meat plants, hotels, restaurants, casinos, and cruise ships are facing higher infection probabilities and higher reproduction number, which means they have higher potential to result in serious outbreaks. We can also find that common areas with high occupant density, like the dining rooms in long-term care facilities or hotels, are facing higher potential of virus spreading. For K-12 classrooms, a teacher is much more likely to spread the disease to the class members than a student patient. This is also consistent with the real data. For college settings, gyms, dining halls, and Greek houses are exposed to very high infection risks, much higher than studying spaces. For meat plants, super spread event is likely to happen in the meat processing room with dense employees. Casinos have a very high potential for super spreading outbreak, considering the high intensity activities and crowded occupancy. Cruise ships have the highest infection risk among transportation scenarios, since it contains casinos and dining spaces where virus can spread already. For transportation scenarios, infection risk during shorter transits are typically lower than the risks during longer transits. Considering that airborne transmission risk is highly dependent on indoor ventilation, we compare the ventilation per person in the baseline cases, which is designed based on the ASHRAE 62.1 standard. It regulates the minimum ventilation rates based on the estimation of required ventilation per person and per floor area. When it is used, ventilation delivered to each person in scenarios with higher occupant density is generally lower than the ventilation in scenarios with lower occupant density. Therefore, indoor ventilation design based on these ASHRAE standard may not always be sufficient for occupants, considering the requirements for mitigating infection risks, especially for rooms with high occupant density. A health-based design criteria for indoor ventilation is probably more applicable for preventing the virus transmission through airborne route. The effectiveness of IAQ conjunctivity is calculated based on the infection risk reduction percentage compared to the baseline cases. We can observe that advanced air distributions like displacement, ventilation, and partitions can have significant effectiveness on mitigating infection risks. Using HEPA filter has a equivalent effectiveness with using 100% outdoor air in the HVAC system. Standalone air cleaners and UVGI system can be an effective solution for infection risk mitigation. Wearing masks is always very useful for reducing infection risks. Except the effectiveness, it's also important to consider the effective scale and cost of strategies. Effective scale will impact the benefited occupant number by the strategy. For example, wearing a mask can only protect one person if he or she is not the infector, but improving HVAC system can benefit all people in the building. Costs include the first investment and maintenance costs. For example, long-term energy consumption or component replacement cost, like filters need to be replaced every 6 to 12 months. An ideal strategy needs to have a high effectiveness, a larger effective scale, which may need to benefit more people, and a affordable cost. Based on our calculation, upgrading HEPA filters and using 100% of air have equivalent effectiveness on risk reduction, but using HEPA filters has a lower cost than using 100% outdoor air, because using more outdoor air requires more heating and cooling energy. Therefore, using HEPA filters is more preferred for HVAC systems. Restricting the building occupancy can reduce the reproduction number of the building, and some air distribution approaches, even though they may have a high effectiveness on risk reduction, but they need professional design and the implementation on professional components, and therefore they may have higher costs. Wearing masks is always very useful, but only works for the personal breathing zone of one person. Long-term use of masks for a bunch of people may increase the cost. These are the main conclusions I just presented. And if you are interested in more details of this presentation, you can check our paperwork for this conference, or you can also access these references we recently published. And if you have any questions, you can contact me or any course of this study. I'm also open to answer any questions here. That's all I have for this presentation. Thank you very much.